In section 5.2, we study the topic of calorimetry, which is the study of heat transferred in chemical and physical processes. So calorimetry can be defined as the determination of the heat released or absorbed during a chemical or physical process. We perform calorimetry in a piece of equipment called a calorimeter. And calorimeters are normally of two types. There are those that are at constant pressure. That means that it's not a sealed vessel. These are often referred to as coffee cup calorimeters because often we'll just use a couple of coffee cups with no lids on them to make these kinds of measurements. And then there are what we call constant volume calorimeters, which are sealed metal containers in which we conduct a reaction. These are often referred to as bomb calorimeters because if the reaction produces gas, well, because it's completely sealed, the pressure will go up quite a lot. So the coffee cup calorimeter is perhaps the most common example of a constant pressure calorimeter. Typically what we'll have is one or two polystyrene cups with some solvent in there, and we'll treat that solvent as being what we call the surroundings, and we'll be monitoring the temperature of the solvent. Often the solvent is water. When a reaction occurs in the solvent, heat will be transferred either into the solvent or out of the solvent, and we can monitor the change in temperature of the solvent. What's important to recognize is that the heat transferred to or from the system will always be equal and opposite to the heat transferred to or from the solvent. So the heat transferred during our chemical or physical process is simply going to be the negative of the mass of the solvent times by the heat capacity of the solvent times by the change in temperature of the solvent. So it's a really convenient way of measuring the heat transferred during a chemical or physical process. A common use for a constant pressure calorimeter is to determine the heat capacity of an object. So this next couple of slides illustrates how we might do this. So what we've got here is a sample of aluminum beads, 23.5 grams, and they're sitting in a test tube that is immersed in some boiling water. That is, the aluminum beads are being heated up to 100 degrees Celsius. Now, sitting in a constant pressure calorimeter, we have 130 grams of water that's at room temperature. And what we're going to do is we're going to put the beads into our water. And doing this makes the temperature of the water rise by 3 degrees Celsius up to 26 degrees Celsius. And of course, the beads are going to cool down from 100 to 26. So the aluminum beads are our system and the water is our solvent. So the heat transferred from our system or out of our system, because our system is cooling down, will be the opposite of the heat that is absorbed by our solvent. So in our case, the system is the aluminum, and the solvent is the water. So the heat transferred out of the aluminum is just going to be the negative of the mass of the water times the heat capacity of the water times by the change in temperature of the water. So we measured that we have 130 grams of water. We know that water has a heat capacity of 4.184 joules per gram per degree Celsius. And our change in temperature, as always, is our final temperature minus our initial temperature. So our change in temperature was an increase of 3 degrees Celsius. So multiplying this out, we can see that our aluminum lost 1.63818 by 10 to the 3 joules of heat. We know this was a heat loss because, well, we've got a negative sign there, and also the temperature decreased from 100 down to 26, so it makes sense that the aluminum was losing heat. Okay, so how does that help us get the heat capacity of the aluminum? Well, the heat transferred out of the aluminum is given by the MCAT equation. It's just the mass of the aluminum times by the heat capacity of the aluminum times by the change in temperature of the aluminum. And we just determined that that was equal to negative 1.63176 by 10 to the 3. So what we can do is we can reorganize this. So if I take the heat and I divide it by the product of the mass of the aluminum and the change in the temperature of the aluminum, and then I'm going to be able to get the heat capacity, which is what I've done here. And when I do that, I get a heat capacity of 0.938 joules per gram per degree Celsius, which is pretty good, and it compares favorably with the literature value of 0.91. There's about a 3.3% difference, so not bad. You know, if you're within 3.3% of perfect on your final exam, you're going to get a 4.0, so that's pretty darn good. Okay, so here's another example. It says a piece of metal was heated to 98 degrees Celsius, so just below the boiling point of water, and then quickly transferred to 50 grams of water in a coffee cup calorimeter. The initial temperature of the water was 27 degrees Celsius, and the final temperature after the addition of the metal was 32.5 degrees Celsius. So it went up by 5.5 degrees Celsius. What is the heat capacity of the metal? And note here, they're not asking for the specific heat, that is, they're not asking for it in terms of per gram, but rather just for the whole chunk of metal. So the negative of the heat lost by the metal will be equal to the heat gained by the water. And the negative of the heat lost by the metal will just be the heat capacity of the metal multiplied by its change in temperature. And the heat that is absorbed by the water is just going to be equal to the specific heat of the water multiplied by the mass of the water multiplied by the change in temperature of the water. So I hope you can see that there's really only one thing that we don't know here, and that's the heat capacity of our piece of metal. So we can rearrange and get this expression for the heat capacity of our piece of metal, and then we just put our numbers in, making sure that we have no issues with our units, and we're going to get the heat capacity for our piece of metal. So the specific heat of water is 4.18 joules per gram per degree Celsius. We have 50 grams of water. The final temperature of the water was 32.5. The initial temperature of the water was 27 degrees Celsius. And then we have to divide that by the change in temperature of the metal. So the metal ended up at 32.5. And it started at 98 degrees Celsius. So provided we put everything into the calculator correctly, we get this answer, which says the specific heat of the, not the specific heat, sorry, the heat capacity of the metal is 17.5 joules per degree Celsius. So this is for the entire piece of metal. It's not for 1 gram of the metal. The second type of calorimeter that you might see is often referred to as the bomb calorimeter. A bomb calorimeter is an example of a constant volume calorimeter. When we're using a constant volume calorimeter, the calorimeter itself and all of the contents of the apparatus that makes up the calorimeter are treated as the surroundings. Bomb calorimeters are often used to study combustion reactions, and combustion reactions are where we have a substance reacting with oxygen and it produces heat. So a typical setup for a bomb calorimeter experiment would be that we have our bomb, which is a rigid wall piece of metal. Inside this we put our reactants. If we're studying combustion reaction, we'll fill the bomb with high pressure oxygen. We'll then seal the bomb off so that the volume is constant, and then we'll place the bomb into an insulated water bath. Once we've got the bomb in the water bath, what we'll do is we'll initiate the reaction, normally using an electrical spark or something like that. It'll go boom, because we've got a high pressure of oxygen there. Heat will flow out into the water bath, and we'll measure the change in temperature of the water bath, which represents the change in temperature also of the calorimeter and everything else that's sitting in the water bath. So it's kind of the same principle as a coffee cup calorimeter, but because we're using gaseous reactants and we're producing gaseous products, we have to keep everything sealed. So that's why it's a little bit more complicated. The same thing applies though. The negative of the heat lost or gained by the system will be equal to the heat lost or gained by the calorimeter. Now, the heat lost or gained by the calorimeter is easily calculated because each of these calorimeters will have a particular heat capacity, often referred to as the calorimeter constant. And this heat capacity multiplied by the change in the temperature of the calorimeter will give you the heat absorbed or lost by the calorimeter. And of course, if we just take the negative of that value, we get the heat lost or gained by our system. So really, we can measure how much heat is lost or gained by our system by just making one simple measurement of the change in temperature of the calorimeter. So it's a pretty simple device. So here's an example calculation using some bomb calorimeter data. So the problem reads, combustion of 1.20 grams of C9H8O in a bomb calorimeter, and then it gives you the heat capacity of the calorimeter in kilojoules per degree Celsius, produced an increase in temperature of 12.79 degrees Celsius. And that's not surprising, right? When you burn something, it's going to release heat. What is the heat transferred during combustion of the compound expressed in kilojoules per mole? And I kind of highlighted this because I wanted to draw attention to the units here. The units are not just kilojoules, they are kilojoules per mole of reactant. So what we're going to have to do is calculate the heat that was released by our reactants, but then divide that by the number of moles of our reactant. So how we're going to express the heat here is we're going to calculate how much heat was released, which will be the negative of the heat capacity of the calorimeter multiplied by the change in temperature of the whole setup. But then we have to divide that by the number of moles of our reactant in order to have it in the correct units. So we're going to be using this data up here to get the number of moles of our reactant. So if you recall, the number of moles of something is just the mass in grams, which we're given, over the molar mass, which we can calculate using the formula, because we know we have 9 carbons, 8 hydrogens, and 1 oxygen. So we put all of that together, and we determine that we have 9.08 by 10 to the minus 3 moles of our C9H8O. So now we can go ahead and calculate the heat lost by our system in this reaction. So it's going to be the negative of the calorimeter's heat capacity multiplied by the change in temperature of the whole setup divided by the number of moles of our reactant. And when we do that, we find out that our reactant lost 5.13 by 10 to the 3 kilojoules per mole. So that's a pretty standard kind of problem, and these bomb calorimeters are often used to figure out the energy released when a substance is burnt, just like this. Here's an example from the book. It reads, how many milliliters of water at 23 degrees Celsius with a density of 1 gram per milliliter so that's just really saying that however many milliliters you have, that's how many grams you have, must be mixed with 180 milliliters of coffee at 95 degrees Celsius so that the resulting combination will have a temperature of 60 degrees Celsius. Assume that the coffee and the water have the same density and the same specific heat. So let's divide this into two sections. We've got the water. The water has an initial temperature of 23 degrees Celsius, a final temperature of 60 degrees Celsius. It has a heat capacity of pure water, which is 4.18 joules per gram per degree Celsius, and the mass is unknown. The coffee has an initial temperature of 95 degrees Celsius. It has the same final temperature as the water. It has the same heat capacity as the water. But we know the mass. We have 180 mils, and every 1 mil weighs 1 gram, so we have 180 grams of the water. So for the coffee, we can calculate how much heat it's going to lose as it moves from 95 degrees Celsius to 60 degrees Celsius. So Q is equal to the mass, 180, times the heat capacity, 4.18 joules per gram per degree Celsius, times by the change in temperature, which is always our final temperature, minus our initial temperature. And you can see that degrees Celsius cancels and grams cancels. So put that into my calculator, and we determine that the coffee is going to lose 26,334 joules. Okay. So what about the water? Well, the water is going to gain that amount of heat. For the water, Q equals mc delta T. Now, we're trying to solve for M, so Q on C delta T will be equal to M. I'll just come up here now. The amount of heat that the water gains is equal and opposite to the amount of heat that was lost by the coffee. So Q will be 26334 joules. The heat capacity is the same as the coffee, same as pure water, 4.18 joules per gram per degree Celsius. And our change in temperature, well, our final temperature was 60, and our initial temperature was 23, and that's going to be degrees Celsius. So joules goes, degrees Celsius, and we're left with 1 over grams. So this is going to give us grams. So that all looks pretty good. So we take that answer from before, and then we're going to divide it by 4.18 times 60 minus 23. And so I'm going here to 2 sig figs. That works out to be 170 grams. And as every gram is the same as 1 milliliter, that works out to be 170 milliliters. So it's almost like a thermal equilibrium problem, but not quite. It's sort of, you have to know your stuff though in order to work through that. Let's have a look at this one. It says a 0.5 gram sample of KCl is added to 50 grams of water in a calorimeter, and then it gives reference to this diagram. That might be useful. If the temperature decreases by 1.05 degrees Celsius, so that means the KCl absorbed heat from the water, what is the approximate amount of heat involved in the dissolution of the KCl? Assuming the specific heat of the resulting solution is 4.18 joules per gram per degree Celsius, and then it further asks, is the reaction exothermic or endothermic? So we can answer the last little bit by looking at the diagram. So the diagram describes a reaction where heat is released into the solution, into the surroundings, as being exothermic. But in our case, everything got colder, so heat was not released into the solution. This happened, right? Heat moved out of the solution into the system, cooling it down. So that tells us that this particular reaction was endothermic. Okay, endothermic. So what that means was that the reactants absorbed heat. And they took the heat out of the water, cooling it down by 1.05 degrees Celsius. So what is the approximate amount of heat involved? Well, we can do this, can't we? Q equals mc delta T. So our mass here is going to be 50.5 because we've got 50 grams of water and 0.5 grams of our sample. Our heat capacity is given to us, 4.18. We can put units in here, grams, this is joules per gram per degree Celsius. And then the change in temperature, well, it decreased, so it needs to be negative, by 1.05 degrees Celsius. And you can see that all units except for joules cancel. We want to make sure that we have the correct number of sig figs here. That has 3, that has 3, that has 3, that has 3. Everything's 3 sig figs. Let's see what we got. 50.5 times 4.18 times negative 1.05. So this ends up being to 3 significant figures minus 222 joules. So that was heat that was taken in by the system. So I think that, and what we've calculated here is the heat lost by the water. So we want to say that the heat of our reaction is the opposite of that, it's the negative of that. So our system gained 222 joules, and the water in which the substance was being dissolved lost 222 joules. Okay, so that concludes the video on calorimetry. I hope you found it helpful.